Wel, noswaith dda, good evening. Croeso cynnes enfawr I Brifysgol Wrexham, I staff, myfyrwyr ac aelodau'r cyhoedd. So, a very warm welcome to staff, students and members of the public to Wrexham University. Fy enw I yw Olivia ac rwyf yn enw hir, diwtor sgiliau iaith academaidd a diwtor sgiliau Cymraeg yma yn y Brifysgol. Felly mae'n fraint fawr cael rhannu noson hyn gyda chi gyd hen yma. So my name is Olivia, and like I said, it's a long job title. But I'm a Welsh language skills tutor and academic skills tutor here at Wrexham University, so it is an absolute privilege to be able to be here to share this evening with you all tonight. Bydd y darlith hon yn cael ei gyflwyno yn y Saesneg. Fodd bynnag, yn ystod y sesiwn cwestiwn ac ateb ar ddiwedd y ddarlith, mae croeso I chi ofyn cwestiynau Cymraeg a byddai yma I gymarthwyo gyda cyfieithu ac unrhyw cwestiynau ac ymatebion. So this lecture will be conducted in English. However, during the Q&A session at the end of the lecture, questions are welcome in Welsh. I'll be here to assist with translating any sort of questions or any sort of statements as well. Rwyf yn awr trosglwyddo at yr athro Paul Davies, a fydd yn cadeirio darlith heno ac yn gyflwyno ein siaradwyr. So now I'll be handing over to Professor Paul Davies, who will chair tonight's lecture and introduce our speakers. Diolch, Alan. Thank you very much.
Diolch, Olivia. Thank you. Noswaith dda pawb, and welcome to Wrexham University. As Olivia said, my name is Professor Paul Davies, and I'm Deputy Vice-Chancellor at Wrexham and have been for 18 months. I do have a housekeeping note to go through, so we're not expecting a fire alarm, but in the event of an alarm, make your way to the nearest fire exit, and the research office staff will escort everyone to the car park. So, we're here this evening to mark the conferment of the title of Professor of Aeronautical Engineering on Rob Bolam. Rob is an aeronautical engineer and an academic with more than 40 years' experience across the industry and higher education. A chartered engineer, a fellow of the Royal Aeronautical Society, and a fellow of the Higher Education Academy. Rob's career includes 24 years in the aerospace industry, both as a professional engineer and as a CEO. And during this time, he led national and international aerospace projects and developed expertise in aircraft design, propulsion systems testing and certification. He also brings more than 20 years of experience in higher education, teaching across all levels of engineering, and supporting the development of future engineers. At Wrexham, Rob has played a key role in establishing uncrewed aircraft systems and electrical propulsion activities, and he created and led the MSc in UAS, developed advanced research laboratories, and supervised PhD research. Through this work, Rob has helped to position Wrexham University as a recognised contributor in the field of zero-emission aviation, both in the UK and internationally. He has also led a consortium of 6 UK companies in the development of the rim-driven fast fan propulsion technology, and his work continues in advanced sustainable aviation and supported by strong links with industry, government and research organisations. I would say that my experience of Rob's research has always been one of awe. Whenever I hear him speak, it is always my favourite stop on the tour of dignitaries, Rob, when we're taking people around the campus, and we always stop with the fast fan with your work. And every time I feel like I learn something new, and every time the level of innovation and your passion for the subject really shines through for me, and it draws you in. It draws me in, certainly, and I see it with others as well. So I think this conferment is a fitting recognition of Rob's contribution to engineering and education. So without further ado, would you please join me in welcoming Professor Rob Bolam to give the lecture.
Thank you very much, Paul. Very kind words, thank you. And thank you, everybody, for coming along this evening. You know, I realise you've got other things you could be doing, but you've taken the time to do this, and I appreciate that. Thank you very much. So tonight's lecture, this is an overview of what I hope to get through in the time we have. So a little bit about the early years of my life and growing up, my education and the formative years. A discussion about industrial career, what I've done in industry, the 24 years that Paul mentioned. I'm not going through all 24 years of them. It will just picking on certain subjects which might be interesting to you, I hope. And then the academic career in further education and higher education. I worked at College Cambria prior to coming to Glyndŵr University or Wrexham University. And then talk about research at Wrexham University. And then future challenges and opportunities which are kind of facing us all at the university in our job and what we can look at, particularly in engineering. And then some acknowledgements, because like anything in life, it's not an individual's journey, it's everybody. And there are a lot of people in this room who've, I think nearly everybody in this room, from what I can see, have played a big and important part in my life. So the early years. I was actually born in a caravan, and I got a lot of stick for that when I was at school. And it was a Dovedale caravan, which now is part of Pemberton Caravans. It wasn't because we were on holiday, we actually lived in the caravan. So it was, and that was because my mother and father, my father was in the Navy, the Royal Navy, as an aeronautical engineer. He was an aircraft artificer in the Royal Navy. And my mother, Julie, in this photograph, they've just got married in Bishopbriggs, just outside Glasgow. And my father's 21 and my mother's 19. So that's how it was in those days. Within no time, there was a conflict. Well, not a conflict. Singapore was getting what they call independence, and they asked the British government to give them some support military-wise so that they weren't overtaken by Malaya or Indonesia, and there was a crisis there. So they sent an aircraft carrier, very similar to what's going on these days. They sent an aircraft carrier called HMS Eagle out to Singapore, and my father was out there supporting that as an aircraft engineer. And this far photograph, you may notice, that's not my mother. When my mother and father moved from Singapore, from the caravan to Singapore, their life really changed. They ended up living in a nice bungalow, and we had a nanny. So it was an extreme change for them. And the nanny here is Lynn, and Lynn brought my sister and myself up, spent a lot of time with us. So the first words I understood and could speak were actually Chinese, not English, which I thought was unusual, but of course most people speak Chinese before they speak English, don't they, in the world? So anyway, when we came back, I moved to Connors Quay here in North Wales and grew up in Connors Quay and also in Caerwys. And Caerwys is a small village, well, it looks like a village, but it's actually a town. Used to celebrate the fact that it was the smallest town in Britain because it had 801 population. Had a town with a town mayor and a medallion and everything. But of course, it's probably not the best thing to celebrate that you're the smallest town, really, because it had a royal charter that went back a long way. A very interesting town. And I lived there, and this is a photograph of me with my space hopper that would be the early 70s. And really, I put the photograph in there to show you that's kind of the nice childhood I had. It was very secure, it was very good. I was happy. I remember that hot day, and I remember how hot the space hopper was. And I was giving it a big cuddle because I just enjoyed that feeling. So it was a nice, good way to live. And here is another photograph of me and the Scouts. And this gentleman here, this young lad, is actually sat here tonight. Put your hand up, Dave. So you didn't know you were going to get embarrassed like this. Yeah, you still got your hair, yeah, so that's a good point. More than I've got it. So, and this is David, and we're at Scouts getting awarded. We're getting awarded a rock climbing badge at NAMPBH, and I do remember this now. And This lady's called Sue Applewhite, and I meant to ask one of the guys who used to work here, Richard Applewhite, if he's actually related to her. Sue Applewhite was a pioneer in her field. I didn't know that at the time, but she pioneered and opened a lot of the slate caverns in Wales, which, because she did slate potholing and caving, and she took us, she was actually the instructor for this course, and she took us down loads of deep mines, and it was quite adventurous. But she's still doing it, and I think she's still running the North Wales Potholing Society, whatever it is. But yeah, really nice. I've mentioned some people here, and their names. One of them's Joan Walker, and she was a person, you know, all the neighbours and people, the adults who I got to know or had influence on me when I was young, had all been in the war, and the Second World War had kind of shaped the way they are and their values. And I've put some names down here. None of them, sadly, are with us anymore. But Joan Walker had a big influence on me. She was a neighbour, and she was from Yorkshire, and she'd worked in the underground offices in Westminster during the war. She was a secretary to Manny Shimwell. But I can remember her telling me about Churchill and Attlee. She actually met them and knew them, and she told me what they were like as people, which didn't really mean a lot to me then, but I do remember what she said. I won't say anything here because it's not really that nice, some of the things she said about them. So, Tom Powell, Dave would know Tom very well, and Tom Powell, well, he was always helping and doing things. Really good man, very brave man, but he was at Dunkirk, and he got taken out of Dunkirk as he did with the when they left, he evacuated, and then he went back for D-Day as well, which I think is a very, very brave thing to do, but extremely modest. Mags Owens, this is Dave's mother actually. She played a big part in our lives, and she had moved to Wales when the Nazis invaded Czechoslovakia. It's a very, very powerful, intelligent woman. And Vaughan Davis, who was our headmaster, was also our maths teacher. We were in a very small school. He was a navigator on Sunderland flying boats over the North Atlantic. So they were very, very influential people on life. But so I left school at 16 and decided that I'd be a stonemason. And that didn't work out very well because it wasn't paid a lot and I didn't get a lot of jobs either. So I had a go at being a gardener, and then I had a go at being a joiner's mate. And the joiner's mate thing was all about glue and chipboard, so that wasn't going very far. And even the joiner turned to me and says, "Why are you doing this? Go and get a proper job." So I thought I'd go back to college. And luckily, we had a college called Deeside College, which is would teach you A-levels. You know, if that wasn't there, that would have been it. You know, I'd have left school and with no chance of getting back into education. But the college had opened in the 50s, and it was there. So I went to do some A-levels. And when I got down there, because I got good results in things like maths, physics, chemistry, stuff like that in my O-levels, they said, "Well, why didn't you apply for apprenticeship?" So I did, and I was lucky enough to get an apprenticeship with British Aerospace. And I worked on the shop floor for 3 years, building aircraft, 125 jets. There we are. So this is the track at Broughton at about the time I was there, and this is a wing. They were just starting to do wings. We did about two wings a month at the time, and now they make about 50 a month. So that's the difference in the wing production, and they don't make any jet aircraft. And working on the track was really interesting. I worked there for 3 years, fitting engines and hydraulics and wings and riveting and drilling. And then I worked in the drawing office for a couple of years. And we stood at drawing boards just like that. That's exactly what it was like when I was there. These days it's all CAD. So I used to draw all my drawings in the past and repairs, write letters by hand and send them off. And this is a photograph of myself with the apprentices I was with at the time. And we're all standing on an aircraft which we had at the college called a Swift, a Supermarine Swift. That type of aircraft actually set the world speed record in the 1950s with a pilot called Twiss, who I met. I was lucky enough to meet him and talk to him. When I came out my time, I worked for a couple of years, or a year and a half actually, in the factory, in an office like this office, right in the centre of the factory. It was very noisy, dusty, and there were rivet guns going off everywhere. So I spent 18 months doing that, and I worked on 3 main projects when I was there. I was the quality engineer for Airbus wings. There weren't many wings, but doing the wings on the Queen's Flight, 2 of the Queen's Flight aircraft, and executive jets. And with the Queen's Flight aircraft, which I always mention that, and people say, oh, that sounds posh. It wasn't. All I had to do was turn up at an office, a Nissan hut on the side of the factory, and there was a military man in there. I'm not quite sure which military he was in. He was always in a suit. And he used to just tell me a whole list of things that we're doing wrong. Then I had to go and tell the foreman and the chap who ran that section what we have to change, like put barriers around it, make sure nobody's got any loose clothing and things like this, you know. And basically, I was just taking a load of faults from one person to another person, and it got argued at both ends. You know, the foreman used to swear at me, and he used to swear at me, so that's what that job was about. And so I decided to leave that job, and I wanted to get into design. I always wanted to be in design, and really Broughton's all about production, and it still is. That's why it's still there, because they produce things well. But I wanted to get into design. So in the design that I did, I knew a lot about structures of aircraft because we built them, and I knew a little bit about Kevlar and composites because they were also on the Airbus aircraft. And they gave me a job in Germany to run. I was quite young at the time. I was 23 when I went out there, to run a group of gentlemen, 6 of them, 5 or 6 of them, to do repairs. And these were the first primary structure. And for those of you who aren't aircraft engineers, primary structure is structure that if it breaks, the aircraft will crash. So things like the wings and the tailplane and things like that. And the vertical stabilizer was in fact primary structure. That's the vertical stabilizer of the tailplane that got where the rudder's on at the back. That was primary structure, but made of composites, made of carbon fibre. And I really just thought about repairs, and between us we came up with a load of repair schemes, drew them up, and we just copied the layup of the composites that was already there, you know, that you're repairing the same orientation, and thought of ways that we could do this with wet layups, pre-pregs, and also with pre-cured materials. And in order to do it quickly, to get an aircraft, you needed special equipment to do this, so it could really only be done at, let's say, somewhere like Lufthansa in Frankfurt, their main centre. So in order to do this, to get an aircraft there, we also did set repairs, which you can use for 50 flying hours. And we basically used the strongest metal we could, which was titanium, and bolted titanium on instead. So those are repairs. I put this boat picture in here because I like boats, and I went to work and came back from work every day on a boat like that, which made the job absolutely wonderful. I was in my element doing that job. But I got fed up with structures after 18 months. We produced 2 structural repair manuals, or chapters for structural repair manuals for Airbus, which were the first ones for primary structure ever for commercial aircraft. And not knowing it, but having looked at it since then, all the other companies like Boeing, the big companies, have basically just copied them. Copied the which we would have done if they existed as well. So it's quite a good one to see. So I wanted to get into systems rather than structures, and I was lucky enough to be able to transfer within MBB which this German factory that I went to work in was called. It's now called Airbus. But MBB stands for Messerschmitt Bolkov Blohm. So Messerschmitt, a lot of people have heard of Messerschmitt. My grandfather, who used to be on anti-aircraft guns during the war, couldn't believe I was going to work for Messerschmitt. So he said he spent most of his time trying to shoot them down, and I was going there to build them. And what I did there was I was lucky enough to get into a group which did environmental control systems, and there were 6 of us in the group, and we were designing them. And the environmental control systems are actually air conditioning packs, which are in this area, and they take bleed air, which is air coming from the compressors of the jet engines. The air goes through an environmental control system and then goes into the aircraft, and then you pressurize the aircraft by controlling how you let the air out of the aircraft, if that makes sense. So the aircraft's pressurized so that people can breathe in it when they're flying around. And my job was to work on the pressurization system for the Airbus A330 and 340. And I had in particular these screens here. These are called the ECAM system, Electronic Centralized Aircraft Monitoring System. And they have about 12 different pages which can be called up. And if you look at it, there's some graphics there. They're called synoptic diagrams. And those synoptic diagrams are generated by the systems that they're actually monitoring. So all the numbers and colors are all generated by the systems. And my job was to do the 4 systems for the air conditioning system, the pressurization system, the bleed air system, and the cruise page. So all those, and we had to tie those into the software, so we did software requirement documents and things like that. One of the other things I worked on was the overhead panel. This is above the pilot's head. And one of the things which I noted when I first got the job was this thing called a ditch switch, which you can see there. And I didn't know what this was, and I was too scared to ask, so I did ask in the end. I said, what's a ditch switch? And they said, well, when the aircraft's going to crash on the water, the pilots have to press that switch. I said, you're joking, right? And I thought, was that stop it crashing? And they said, no. Said it closes all the valves which are open and closes all the holes below the flotation line of the aircraft. I thought, that can't be right. Aircraft, you know, I'd seen a video of an aircraft trying to land on the sea. It was a remote-controlled large aircraft, and it just cartwheeled down the sea and broke up. I thought it must be impossible to land. And we actually had conversations about it, and they did some tests on a water tank. They showed how an Airbus should go into the water, how it should go in tail first, hit the water, and then slide along and glide, and then it will sink. And I still found it very difficult to believe it was possible to happen, until it actually did happen in the Hudson River on an A320. And the first thing I went to do was find out, did they press the ditch switch? And he didn't press the ditch switch. And if you look at it, it sank not long after. Had he pressed it, and I thought he did a brilliant job in landing the aircraft. I was, you know, not taking anything away from how brilliant the guy is. Had he pressed it, probably wouldn't have sank so quickly. Stayed afloat a bit longer, maybe. So after that, I was keen to. I worked for about 4 or 5 years in Hamburg, in Germany, and had a fantastic time. And wonderful people, brilliant engineers. Really enjoyed the time. Really good. But after that, I wanted to get back to the UK and work on smaller aircraft. And I went to work on this aircraft called the Jetstream 41. When I went there, it was a blank piece of paper. Within 2 years, about 120 engineers had designed this version of the Jetstream, which was extended. And this was the very first aircraft to fly. That's the flight number 1, or the aircraft number 1, production test aircraft. And it had to be tested in icing conditions. And my job was to design all the icing systems for it, ice protection. So I wondered how I got that job, because it was really, it was quite an important job to get at a fairly young age. And I was about 28 when I got this job. And I realized within no time it's because it's dangerous. And What you have to do is, after you've designed the ice protection systems, you've got to go to Iceland and fly in clouds between Iceland and Greenland until you've got loads of ice on the aircraft and see if your systems work. And I was 28, and I was one of the oldest people on the aircraft. All the other guys on the aircraft were much younger, except the pilot, who was 32. But he was always in the pub. And not to bring it, he was an excellent pilot. They were a really good crew. And just to give you an idea of what we're doing, there's some shapes here. We used to fly and get 3 inches of ice on the aircraft and 1 inch on protected areas like this, and then operate the systems to see if they worked. I had to log all the droplet size in the atmosphere, the temperature, the speed we were flying, the altitude we were at, all these things. And we had to fit it with instrumentation beforehand, which I did with, if you look at the top of that aircraft, it's got a thing sticking out, which is called a Nollenberg particle detector, laser-type particle detector. So flying on this aircraft, there were a few things dangerous. There's a dangerous ice accretion here. This is a story which I learned a big lesson from, actually. I designed, all this area is heated, and that's why there's no ice on it. And I designed the heating to go around this area as well. But I was in a meeting. To do that, it takes a lot of energy out of the aircraft. It takes a lot of air. And I was in a meeting, and the 2 guys with me, one was the chief engineer and the other one was the technical director. And they said, you can't have that much air, so cut that bit. We don't get ice there on the Jetstream 31, cut it off the 41. So I did, but we actually, it was already built into the structure, but I cut the air supply to it, or in the design, we cut the air supply to it. And then we went flying, and it just started to accrete ice. And I remember looking at it through the window. I'm actually on this aircraft with the pictures taken here. I'm about halfway down the cabin. And I was looking at it through the window, thinking I knew that was going to happen, but I haven't done anything about it. And with the aircraft, it happens on both sides. So I've got this ice on both sides, and I know the amount of ice on the aircraft then was enough that if it went down the intake, it would crash, the engine would get damaged. And so I called the pilot to come and have a look at it. And he came over, and we were both watching it, and it just rattled loose and went down the engine. And we heard a crash as it went down the engine. The engine whirled down and then shut down, and the whole aircraft slewed and fell quite a few thousand feet. By the time I'd got back into my seat, the pilot had already got back into his seat and pulled the aircraft out, and we were about 2,000 or 3,000 feet above Surtsey in the Atlantic. So yeah, that's the Empire Test Pilot School for you. They were really quite cool about it. But we went back and fixed it, and the engine needed repairing. We had to change the engine, actually. But yeah, so quite exciting times. But then I got a job at Rolls-Royce working on engines. And I've put these 2 pictures here to show you one of the engines I worked on, which was the design of the BR710. This is what's called the core of the engine. And just to point out, because it will come in useful later, this is the fan at the front of the engine. And most of the air from the fan goes around the outside. Some of it goes down the inside. If 1 kilogram of air went down the inside, 4 kilograms on this engine would go down the outside. It has a 4-to-1 bypass ratio. The stuff I worked on was none of that. It was all the stuff on the outside called the core-mounted equipment. So I worked on all those systems. And that was really interesting. But we learned a lot about how these engines work and the design of the blades and such like. And then I got another job which involved an engine. When I was doing these jobs, I actually had started my own company by then, so it was through consultancy, and I had other folk working for me, doing some of the jobs, so we could take on larger jobs. And this one was a reliability study. In actual fact, by that time, my wife had got an HND at Newey in mechanical engineering. Who's here? Put your hand up, please. And she's very good with mathematics and figures, and she was doing the reliability calculations for this. We were setting up the systems and how they worked, and she was doing the calculations. And this is, if anybody knows what a JSF fighter is, F-35, they're actually in operation in the Air Force. this is essentially how it works, and this isn't top secret at all. You can get this on the internet. There's an engine, and it drives a shaft into a clutch, and it drives 2 fans. And the fans contra-rotate. And it produces all the thrust for an aircraft to take off vertically. And there are 2 types of aircraft. There's the F-35 that you might know now, but before that, there was the concept demonstrator aircraft, which only had to fly for 150 hours. And this is the one I worked on back in the late 90s. And what my job was, or the team I had working with me at Altitude Products, my company, was to do the reliability studies and design input into the clutch engagement unit, the fan vectoring nozzles, and the variable guide vanes for the jet engine. And those units, that was a really interesting job, but it made me think about the vertical takeoff and the fan arrangements, and that will come in a bit later. So as I mentioned, Altitude Products, I had a company based in Denby, an industrial estate in Denby. We had all the offices here for design and calculations and whatnot. And this unit alongside was a machine shop where we made components for aircraft. Sort of aircraft we worked on, there was the first unmanned aircraft I started working on that time, which was in the Army. And I did de-icing systems for it, because the MOD asked me to design a de-icing system for the Phoenix UAV. The Phoenix UAV was an awful unmanned aircraft. It was too heavy, too slow, too loud, and really expensive. By today's standards, it's really bad aircraft. And they've got rid of them now. But the thing is, they used to crash them a lot because they used to land on a parachute, and more than ever got blown into trees. And so they were damaged quite a lot. So you can see some of the chap who used to work for the company called Chris Bluff. He was a student here at Wrexham University, and I took him on in the company to work with us. And we're testing a de-icing boot, which is on the tailplane of that aircraft in this picture. And we patented that system. And then I worked on an aircraft project called the Boeing Sonic Cruiser. And that was the first more electric aircraft. So the jet engines drove electrical generators, which we used to drive the air conditioning systems and all the power systems. And that way, it gave me the idea of looking at more electric propulsion. So that and the lift fan project were formulative in this, looking at the research which I was going ahead with. The final job I worked on the aircraft world and industry was actually the Nimrod, which was built at Woodford. It was the last aircraft to fly out of Woodford. And it flew on August 2004, took off and flew out of Woodford, and they closed the airfield down after that, and now it's a housing estate. And in September 2004, I started working at Coleg Cambria. Some of the research I'd started to look at by then was rim-driven fans. Because of what I'd seen with the lift fan, I thought that would be better if it was electrical and not mechanically driven. And looking at the work like that. And so here we can see the first patent I put in on a rim-driven fan back in 1999, which is nearly 30 years ago. And this was the first unit made in 2016. The reason why I didn't pursue this back then was it was impossible to do by the time I'd looked at the circuitry required, and the state of technology at the time would have made it too heavy. And then I worked, I thought I'd spend some time with my family and having more relaxed time as they were growing up. So I took a job in doing further education, put more back into the apprenticeship program that I came through on. And I worked for 9 years heading up the City and Guilds program for the Airbus apprentices and Thomas Cook apprentices. So we did maintenance and craft apprenticeships. And I also taught on the HND programs there, which were run through this university. And this, again, is the aircraft which I was standing on when I was an apprentice, the Supermarine Spitfire. In the back is a Gannet. And the Gannet, in actual fact, that Gannet had been on HMS Eagle many years ago. So when I moved to Wrexham University, one of the things which became evident was that unmanned aircraft were going to be prominent. So I set up an MSc course on unmanned aircraft. And for each course I made, and you do this for courses, I had a funding model. How's it going to be funded? And this is just, I put that there just to give you an idea of what a funding model looks like. You don't just do an MSc module or MSc course. It has a life of its own. We taught people how to fly drones when they needed PIFCOs up at Northup on the flying fields. We taught lessons on navigation. We taught them how to build drones. These are students here at Wrexham building drones. And this is a lecturer who used to work at Wrexham programming a drone. And then we used to interface with STEM events and industry, with the local environment people doing 3D modelling of Mulvami, for instance, if people know where that is, up in the Clwydyn Mountains. We did the first 3D model of that. And competitions. Here's the unmanned aircraft competition. This gentleman here kindly sponsored us in this competition, and he is here in the front row today. Thank you, John. And this lady, Sue, who's not here at the moment, she also sponsored us, who ran an insurance company in Liverpool. And we did conferences as well. Oh, here we go. Well, this is the Fast Fan, and it's a project which we've done here at the university, and very pleased and proud that we're getting somewhere with it. In the room, I think Paolo at the back in the room worked as a research assistant on this, and now works full-time in the university. And this is what it looks like inside. So, and if you look at this blue part, that's an interesting thing to look at the moment. That's called the stator, and it supports 2 fans. Just to give you a rough idea how the fast fans work, the motor's on the outside, so they can be cooled down easier, and they can put more energy into the airflow. So the energy comes into the air, flows through the engine. You can put energy in an engine through the fan. It's a very good way to do it. And then constant rotation of the fans makes sure that it's done very efficiently. But that's led us on to the area we're looking at now, and now we're really talking about the research areas we're doing a lot of work in. One of the projects we're looking at is a thing called an electrothermal fan engine. An electrothermal fan engine is one that, instead of having two jet engines like that, you replace the 2 jet engines with 2 fans, and you have 1 jet engine. So you've got 1 engine that's burning fuel. The thing with the jet engine is that all the air that goes in, if you remember, there's a bypass ratio. Some of that air that goes in there goes through the engine and gets burnt with fuel, and the exhaust gases get mixed up with the air as it comes out the back. What we want to do is get rid of that and avoid that. So the way we do it is to have pure air coming into the engine, the jet engine, and pure air coming out the back. But in the middle, we have a jet engine running generators, which run the fans, and the exhaust heat, which is normally wasted on a jet engine, is captured and fed into these jet engine stators, into this blue part, which is hollowed out and is a type of heat exchanger. And that's got really good advantages. One of the big advantages is that the aircraft looks the same. If you were to get on as a customer, a paying customer, or as an airliner or an operator, if you had a business jet, you could make a business jet with the electrothermal fan engines. Although it's only got 1 jet engine, it would look like that. And it would be safer, or just as safe as existing business jets. We can prove that through reliability studies. So we can get, our calculations show that we can get about, for this type of aircraft, this arrangement, we can get about 111% increase in effective bypass ratio. And that's because we have 1 jet engine now with 2 fans, not just 1 fan, but 2 fans pushing a lot more air back. That's important in aircraft propulsion because the high bypass ratio gives you high propulsive efficiency. And the fact that we use the heat as well from the exhaust and feed that into the jet engine, that gives you high thermal efficiency. And if you multiply the propulsive and the thermal efficiency together, you get the overall efficiency. And the overall efficiency of a jet aircraft like that is somewhere between, well, about 40% would be good for a jet aircraft like that. If it had electric thermal fan engines on it, it would be closer to 70%. And that's a massive difference in aircraft engineering. And this is how it works. The air comes into the first fan, goes through a heat exchanger, goes through the second fan, and gets accelerated out of a nozzle. And the nozzle, the air coming out of the nozzle is supersonic. And in engineering, we look at, that's a heat engine. We look at heat engine cycles in a way looking at a thing called temperature against entropy, temperature-entropy diagrams. So from 1 to 2, that's the air entering the engine. It's isentropic. From 2 to 3, it's about 90% isentropic. So it's the fan energy is put across very, very efficiently. If this line's going straight, it means it's efficient. When we come to the middle part, and we're using the energy that's otherwise wasted, this line, the angle of this line depends on its efficiency, or the length of the line depends on its efficiency, really. This is the heat energy going into it, and then the second fan, once again, lifts the temperature right up high. When we get to 0.5, that's where that shows how much energy we put into the system, and that isentropically accelerates through the nozzle to give us the thrust. And that's the first time, in actual fact, that type of thermal diagram's ever been created and shown, actually. So that's a new one. And this is, when we look at aircraft, we do payload versus range. This is that existing aircraft. That was a Citation type jet. And this is what we would get if we had the same sized aircraft with electrical thermal fan engines on it. A range extension of about 33%. And to look at that in pie chart ways, what we'd actually have is that we'd have the gas turbine engine fan normally would be taking about 928 kilojoules per second, and then the exhaust heat waste would be 1,300 odd joules per second. In our case, our electrical fans would be 670 joules per second, exhaust waste would be 563, and the recovered waste is 459. So it makes it an awful lot more efficient, and we're burning less fuel. If you burn less fuel, you can go further, and that's the way it works. So what else are we looking at? Strategic energy storage systems is another area we're looking at. How can we, in this day and age, it's really important that we can store energy and use it when we want it. So what's a practical way of doing that? Well, a practical way of doing that is using aluminium, which is a metal I'm very familiar with because I've been working with it all my life. And aluminium, what we can do is we can use surplus energy from that we generate through tidal energy, for instance, or wind energy, and make aluminium billets out of it, but make them in a way that we can use them in batteries or fuel cells. It's the same type of thing. It's called a metal air battery. The beauty of using aluminium is it's got very high energy density, and also it's light in weight, and it's the most abundant metal in the Earth's crust. And the dielectric that we can use can be salt water, like seawater or concentrated seawater, and then we use air and carbon. So they're all very, very friendly elements which are very accessible. This can be used to store, so you actually store the energy as metal plates, and they're also a commodity on the market which is actually going up at the moment. But we could make large batteries in containers, just like shipping containers, and stack them and put them together in series and parallel. And a large amount of batteries that you'd see on, say, a large container ship would be enough to supply a town probably for about a month, or an island or something like that, and you can ship them around. So looking at future challenges now and where we're going with engineering. And when I look at this, I have two main thoughts. One is more to do with the political environment in which we live, and the other one is to do with the artificial intelligence, which is on everybody's lips these days and how we're looking at it. From an engineering point of view, I see artificial intelligence as being something we should embrace and really work with. It's really important to do that. And I think we've got to get ahead of the curve with artificial intelligence, not just wait till it comes along and determines our futures. A lot of people look at it like the genie's out the bottle, and you can't really put it back in the bottle. So looking at it, I see there's 4 main areas in engineering. One is to do with application, which I think lots of people could buy into quite easily. So we use CAD packages, we use FEA packages, CFD packages, all ways of calculating things. These could be automated quite easily. You could have a CAD package where I just spoke to someone and say, design me a fan, and the machine would design a fan. Then I could say, I want this pressure rise, or I want this diameter, and it would design it, because all the information is available to do that, and that's what we do. So the application's quite easy to do. To validate that, we'd need some kind of independent AI that validates it, because you've got to make sure that what you've got makes sense and the design is real. So independent verification of AI is required, and it's an area that can be worked on. And then there's these other 2 areas, and I'll go for innovation next. Innovation in AI. How can you invent things with AI? Well, that's already been done. In actual fact, there was a gentleman in Russia, Ukrainian-Russian gentleman in the 40s, who actually thought of a thing called TRIZ, and it's called inventive problem solving. And it's a way of making a logical way of inventing things. There are about 40 different processes. He categorized thousands of patents, him and his team, and they got them down to 40 different processes. So there is a way of applying artificial intelligence to innovation, and I would start there if I was to look at that. But then there's this other one, this 4th one, vision. And that's the interesting one for me, because how do you have vision from artificial intelligence? How can it predict what's going to be needed in the future? And that's forecasting the future trends and linking conceptual thoughts to needs. What we need to do, I think, in engineering is be able to address these and really look at them and study them. And that way we can get ahead of them, because what that's going to do is artificial intelligence is likely in engineering and in other fields is likely to need to be looked at from an ethical point of view, in that people's jobs are going to be made less people are going to have work which they usually identify with. So there's an ethical issue there, because humans are affected by engineering decisions. And at the moment, most engineering work, or a lot of engineering work, doesn't really have a big ethical part to it. It's not always considered unless it's directly affecting humans. And I think everything we do along these lines, if we look at that, we need to look at that, the ethical aspect of it. Which, the starting point for that is psychology of retirement, because that's what it's going to be. You've got to think of what do people do when they retire, and when they leave their jobs, and they lose that sense of purpose. That's what's got to be looked at when we start doing these things in parallel. So it's a link with psychology, a link with the social sciences. And then we have the social political change, which is currently going along. And how do we protect and support our values? The type of values which I was lucky enough to experience through my childhood, of things like freedom of thought and expression, democracy, equality, diversity, inclusivity, and sustainability. All those things are values, and I'm sure lots of people here share those values. How do we support that? And that is something we've got to think about within engineering. Luckily, we have now got a whole research lab, and through the great work of my colleagues here, we've also got research degree awarding powers. So we were right in the position to actually do these things and make these changes and investigate these engineering trends and ways, and go ahead with our research. So we have all these facilities. I know that a lot of the people here have got labs. Mo's got a lab that does antenna design, and his work that he's doing is absolutely fantastic. Yuri's got a lab that does power electronics and propulsion. Ian, who's here, he's got a lab who's doing composites. And Paolo at the back is working in the power electronics lab, setting that up and helping with that. So there's a lot of great work going on in the Wrexham University. But I'd like to make some acknowledgements now. And first of all, the kind support of the research department, which has set this up, and it's my fault on the clicker. Yeah, I got the training, but just didn't apply it. My valued friends and colleagues, some of whom are here this evening. The students have been privileged to teach thousands of students now, I think, and all the people who have played a part in the journey so far. The institution of Wrexham University, including its other incarnations, Glyndŵr and Newey. I've been at all of them as a student or as a lecturer at some time. And finally, my family. And on the left is a picture of my mum and dad, Julie and Bob. Bob's the one with the beard. But that's a picture that's dear to me about them. So thank you very much, everybody.